Welcome to the last lecture of the third week. So, today we are going to speak about maxima and minima, that too of several variables. So, essentially I would put myself down to two variables and I would expect that you can make the extension. Maximum and minimum, or maxima and minimum, whatever you want to call it, is a part of mathematics known as optimization. So, this operation of maxima and minima is given a generic name of optima and the subject is called optimization. I have spent my research life trying to understand optimization problems. So, it excites me to speak about maxima and minima. Of course, you can say, oh, you could have written maximum and minimum of several variables, the standard way things are written, but I am talking about maxima and minima. You might be wondering why I am just telling maxima and minima. Please note that there is a very famous saying of the mathematician Leonhard Euler that nothing in this world takes place without some quantity being maximized or minimized. So, optimization is everywhere. Nature supposedly is a big optimizer. So, this is a very important area of mathematics with huge, it is kind of the border area between theoretical math, which sometimes people call pure math, and applied math, which it has huge applications. Very big mathematicians have been involved in trying to understand how to figure out a maximum and minimum of function. It is not so simple. One might look, it might look simple on the face of it here, because we will do simple examples, try to make the theory simple, but whatever it is not so simple as it is. And to start with a little lighter version of the thing, once in New Delhi I met a family which had two lovely little girls, and when I asked them their names, they said maxima and minima. One was called maxima, another was called minima. I was very surprised as an optimizer that parents could give such innovative names, mathematical names. So, here we would consider functions of two variables. And we will seek the definition of minimum and maximum. So, point x naught y naught is minimum or minimizer, is a minimizer if f of x y is bigger than equal to f of x naught y naught for all x. This inverted is a symbol for the word, the phrase for all x y naught 2. So, I am trying to minimize this function over the whole of R2. It is called unconstrained minimization. And maximization, you have the same kind of story. So, x naught y naught is a maximizer if f of x y is less than equal to f of x naught y naught for all x y in R2. Okay. So, this point, this value f of x naught y naught, whatever be x naught y naught, is called the minimum or maximum. It is called the minimum value or maximum value, as is the nature of x naught y naught. This definition actually tells us that these are global maximizers, global minimizer and maximizer and global minimum value. And that is what we really seek when we talk about minimization and maximization. But is it always possible to detect them? The answer surprisingly is no, and that is why we look for what is called local minimizers and local maximizers. For example, you have learnt in your functions of one variable, suppose phi is a function from R to R, then a local minimizer is something like this, that okay, look at, let the function be like this. So here you see locally, for example, if I take this point x naught and take a very small delta, that is maybe. So basically I consider an interval x naught plus delta and x naught minus delta, where delta is positive. So I am considering an interval x naught minus delta and x naught plus delta, and in that interval you observe that is for all x in this interval you have that phi of x is bigger than phi of x, phi value at x naught. So that is what is called a local minimizer, because you come to this point, say x star. So this x star value at this point, the function phi value, the phi of x star is strictly less than the value of phi of x naught. So there is a x star for which the function value decreases further. So this is only minimum or a minimizer in the local sense and not in the global sense. So global means it has to, this thing has to hold for every x in R. Here we show that it, for example, through this drawing at least, that it is not the case. X star is the point where this is broken with respect to phi x naught. So x naught becomes a global local minimizer. So in most cases we will be able to figure out local minimizers and not global minimizers. So what are local minimizers? For a function from R2 to R, for f from R2 to R. So for that we have to first talk about an open ball of radius delta, which we have written earlier. So at a point x, the open ball of radius delta centered at x is the collection of all y in R2. So these are two dimensional y in R2, such that norm of y minus x is strictly less than delta. So these kind of sets are often called as open sets in mathematics, because we do not have the boundary, that is we do not have the points y for which this is equal, right. That is, it is a kind of on two dimension, basically it is a circular disc, something like this, where we have everything inside, but we do not have the points on the boundary, we do not include them. All the nuances of optimization cannot be said in such a small one lecture, but it is a kind of understanding that we want to give you about the subject, that okay. So the notion of this delta neighborhood is now replaced by this delta open disk. So this is called the delta, which is radius, I will call it the delta open disk. So this simply means, so if y is y1, y2 and x is x1, x2, it simply means y1 minus x1 whole square plus y2 minus x2 whole square, this sum root over has to be less than delta. That is the meaning of this. This thing simply means this. And what is the meaning of a local minimizer. So, x naught y naught is a local minimizer of f over R2. So, here we are going to talk about maximization minimization over the whole space, and such actions is usually termed as unconstrained minimization. There is no additional requirement on the points. Minimization or maximization, whatever, or optimization in one go. So, x naught y naught is called a local maximizer over R2 if there exists delta greater than 0 such that for all x in the ball delta around the point x naught y naught so all delta for all x which is in this ball, we must have f of xy to be bigger than f or equal to f of x naught y naught. You have learnt that in order to find a local maximizer or minimizer of a function of one variable, if the function is differentiable, your first test is to find a point which satisfies this. Once a point x naught which is found, which is called critical point, then you know that okay, this is a necessary condition, that what you show that if x naught is a local minima, then the derivative must be equal to 0. That is what, that was a great, one of the greatest works actually Farma knew about this, though for polynomial function, but one really needs to look at the way Farma did it to see the joy of doing mathematics. Now, what happens is that if you just find a point, you cannot say that it is a local minimizer. The first result, it says that if it is a local minimizer, then this will happen. So, which means a local minimizer must satisfy this condition. So, to find a local minimizer, I should seek my local minimizer among points which satisfies phi dash x naught equal to 0. So, once such a point is found, I really have to test it. If I can easily test it, it is fine. If I can't, then I have to go to a second order condition if that is available. So, if this is true, then we declare x naught is a local mean, and if this is true, local max, and there is no conclusion if I just have this to be 0. Usually this is called a saddle point, that is the shape of the curve changes there, like for example y equal to x a cube. The derivative is 0, but the second derivative is also 0 at that point at x equal to 0, and you get no conclusion. So, from this will, so second derivative 0, no conclusion. Can these ideas be brought into the domain of two variables? The answer surprisingly is yes. And I do not want to get into the detailed proof which actually involves the use of Taylor's theorem. So, I do not want to get into the details of that, we will use Taylor's theorem little bit later. But you see that what happens, I am just giving a very intuitive proof, this is not a rigorous proof. The idea is very simple, that when I say that okay, f of x y is bigger than f of x naught y naught for all points for all points near x naught y naught. I am just using, I am not getting this delta stuff every time, points near x naught y naught. Then intuitively it appears, and it is true also, we can show that if I fix my y naught, then f x y naught, because x y naught is also a point near x naught y naught. If x y is a point near x naught y naught, then x y naught is also a point near x naught y naught. So, x of y naught is bigger than equal to f of x naught y naught. So, when I fixed y naught in this function f x y, so it becomes a function of one variable. It becomes a function of one variable. So, function of only one variable x, and what is that? The derivative must be equal to 0 is the necessary condition at x naught. So, del f del x, because just the derivative of this would entail me this thing, that should be equal to 0. Similarly, I can put x equal to x0 and tell the same story, where y naught would become the maximizer or minimizer of the function f of x naught y. So, then that case my necessary condition from what I have written down there for one variable will become this. I have not done this in detail, so please forgive me for being so crude, because we have so less time that sometimes we just go over giving you the ideas of the intuition. So, this is a necessary condition and not sufficient. We are assuming that all points are, all problems are differentiable problems, all functions are differentiable. We are not discussing non-differentiable problems. I think we will shy away from the fact that functions are non-differentiable, but this is a necessary condition. Any x naught y naught satisfying this is not necessarily a minimizer or a maximizer. An example that is given in the book, which is very simple, and it is pretty well done example. So, for example, take f of x y equals to x square y plus y square x. Once you have taken this, take the partial derivatives del f del x and equate it to 0 and see what points you get. Two x y plus y square equals to 0, and del f del y would give me x square plus 2xy is equal to 0. If I subtract these two, I will obtain, this would imply x square is equal to y square. So, this implies to me that x is equal to plus minus y. Now, put x equal to plus y in this first equation. So, it will give me, when you put y here, it will give me 3y square. So, if I put, now I put x equal to plus y here. So, that gives me 3y square equal to 0, and that is implying y equal to 0. If I put x equal to minus y also in this equation, so it will become minus y square equal to 0. This will imply y equal to 0. So, when I put y equal to 0 in both these equations, if I put y equal to 0, so x is plus minus y, so x is equal to 0. So, my only point which satisfies these two equations del f del x equal to 0 and del f del y equal to 0 is x equal to 0 and y equal to 0. But the fun part is that this is not a minimizer, because look at the equation z equal to x square y plus y square x. Now, here I have the point 0 0, which is a critical point. Here I have the point 0 0, which is the critical point and which is not, does not appear to, which is a critical point and the only one. Is it the minimizer? So, let me do a little test. The test is this. It is a very simple test to show that it is not even a local minimizer. Let me consider the line y equal to x. On that line, the function value on, that is on y equal to x, z is equal to, so I am putting y is equal to x, x cube, y equal to x, x cube, it is 2x cube. Now, which means it depends on what x you choose, whether you choose x positive or negative. If you choose x positive, if x is positive, z is positive. If x is negative, z is negative on y equal to x. But z is equal to fxy, f evaluated xy is 0 if xy is 0. If xy is the origin, the 0 0 vector, then fxy is 0. So, whatever, however near you go near x on this line 0 0, there you can always take a positive value or you can take a negative value. The function value either becomes positive and negative in both sides of x. It is not that it is always positive or always negative. So, 0 0 is neither local maxima or local minima. So, 0 0, so here is an important conclusion, x y equal to 0 0 is neither a local minimum or local maximum. So, this shows that this condition del f x, del f del y equal to 0 and del f del y, del f this one, that is del f any point which satisfies this. So, if a point satisfies this, it is only possibly a point which might be a local maximizer or minimizer, it does not tell me. So, for the maximum also I can write the same story which I am not writing. So, it does not tell me whether it is really a local maximizer or minimizer. So, you need additional conditions. What are those additional conditions? One is the second order condition, another is the convexity condition. Convexity is the particular nature of the function which tells us how to what would happen if I just have first order information and I have not used second derivatives. Here I have used second derivatives, but suppose I do not have second derivatives or do not want to compute them, they are expensive to compute. So, I do not do anything. So, how can I get an information? So, that brings us to the topic of convexity of functions of two variables. Without going into much details about convexity history, I can just tell you that this idea was known in 1889, if I am not mistaken of the date, to a Danish, not Danish, I think, mathematician from Holland named Jensen. So, it is sometimes the definition of convexity is called Jensen's inequality, but for the case of functions of two variables and which is also differentiable, a function is convex. A function is convex if I am giving an equivalent definition in terms of partial derivative. A function is convex if for all x y and for all x naught y naught, these are elements in R2, of course, I am not writing that, f of x y minus f of x naught y naught, that is the definition for it, just take it as a definition for the time being. Unfortunately, I do not have time to teach you convex analysis, though that would be a very different game. So, this is greater than del f del x at evaluated at x naught y naught into x minus x naught plus del f del y evaluated at x naught y naught at y minus y into y minus y naught. This is the definition of a convex function. I can give you an example of such a function. Suppose f of x y is x square plus y square, the paraboloid, and this is an example of a convex function. This will satisfy that definition. You can try out with various points, you will see that this definition will get satisfied always. So, this is an example of a convex function. I do not want to get into details, but what happens if the function is convex? So, keep on looking at this electronic slate where I have written down the definition. So, suppose this result, this fact is true, that I have a critical point, that del f del x, sorry this is del f del y, del f del x is 0 and del f del y is 0, that is the two necessary conditions is satisfied and the function is convex, then is x naught y naught a solution? The answer is yes, because if f is convex, then fix x naught y naught and vary x y, and observe from what we have defined and from definition we have f of x y minus f of x naught y naught is greater than equal to del f del x at x naught y naught into x minus x naught plus del f del y evaluated at x naught y naught. So, with the point which is here on the after the minus sign, we have to evaluate the derivatives at those points. Now, if I put del f del x not equal to 0 and del f del y not equal to 0, what do I get? So, here I can vary any x y not 2. So, I get f of x y, because this will be 0 now this side, f of x y is bigger than f of x naught y naught for all x y naught 2. So, what does it say? It says that if you have a function convex and if you have its critical point, then that critical point is a global maximizing value, it is a global maximizer. For example, the critical point of this function is at 0 0 and 0 0 is the global minimizer of this value, not sorry no maximizer, it is a minimizer. So, any critical point of a convex function is a global minimizing value. So, this is a very important statement that we are going to now write down. For a convex function, every critical point is a global minimizer. For a convex function, every critical point is a global minimizer. So, can we tell something like this for the case when we try to find a maximizer? For the maximizer we have concavity. So, what is then concavity? Concavity is a function phi, say, or phi or psi or whatever is concave if I just reverse this inequality. So, let me write down a function say h from R2 to, I am just changing f to h just to keep consistency. H from R2 to R is called concave. Obviously, I am assuming differentiability. Please understand, all functions that we talk about are differentiable. There is no discussion of non-differentiable functions. So, function is called concave if for all x y and x naught y naught in R2. H of x y just reverse this game. We reverse this game and that will give us, so del h del x evaluated at x naught y naught x minus x naught into y minus y naught. Now, suppose I have a point x naught y naught, if del h del x evaluated at x naught y naught is 0 and del h del y evaluated at x naught y naught is 0, it implies from this, because I can vary all the x y's keeping x naught y naught fixed, because these two for all x y and all x naught y naught, and I can put this 0 here to obtain that h of x y is less than equal to h of x naught y naught for all x y in R2. So, what do I get when h is concave? So, when h is concave, every critical point is a global maximizer. So, let me write that down, that when h is concave, every critical point is a global maximizer. Is a global maximizer. So, this is what you will not find in normal calculus text. They do not speak about convexity or concavity, but I have also not done a very fair job, because if I want to talk about concavity and convexity, then it will basically take the, if I go to details, it will take the whole class, actually whole time will go just discussing about introducing convexity. So, we will end the talk here. We will make a little change in our structure. We will push one part into the fourth thing. The second derivative test I will separately teach you. Now, if f is not, or h is not concave and f is not convex, how do we handle or how do we use our second, if there is second order derivatives, if there is second order information, how can I use it to determine in the same way as I did for functions of one variable whether the function is concave or whether the function is having a local minimizer or local maximizer or nothing, a saddle point which I can say. So, that decision can be done using second order stuff, but that would actually entail almost nearly an hour's lecture, and I cannot obviously because of time constraint do it. So, what I will do, if you go to the course syllabus, the one thing that I would have that I would be talking about at the end, the last part would be more about vector fields, which but we can skip that because that will be little advanced for you. I was thinking of putting a little advanced stuff, but it is better for you to do and learn this second order. How do we develop the second order condition? How do you prove what we have? So, it is very important to know how to get a feel of the second order condition is know to do the proof, and the idea is that we can use quadratic functions, that is second order Taylor's expansion, to actually do most of our job. So, because we are talking about second order, we will talk about second order information, we will use Taylor's expansion of order 2 which we did in the last class, and that will take a whole class to explain, and that we will do step by step with several examples, because that is very important and that cannot be done in this little part. So, this was just about introduction of maxima and minima, and just introduce you to these notions of convexity and concavity. So, we will push the vector field section out. I can put that as a special lecture. If everybody wants, you can put it on the portal, we can put it as a special lecture on more on vector fields, but instead of starting the 4th week with Lagrange multipliers, I will talk about second order tests for finding maxima and minima of two variables, of functions of two variables. That would be what we would be discussing, and then after doing that, the next class would be on Lagrange multipliers, and so we will shift the last one will be shifted. So, in that way the vector field would go out, and so this little modification I will let NPTEL know, but it is but as I worked throughout the whole thing, yesterday night I was working out the whole thing, and I realized that it is absolutely essential to have a full class on how to use second order information to determine whether a critical point is a maximizer or minimizer or maybe nothing, saddle point if you want to call it. So, so let it be that way, that is a better method of pedagogy I would say, and let us call it quits for today, and we end the 4th week here, and 5th week we start with the second order test. Thank you very much.